Hello, everyone, and welcome back. In this lecture and the few lectures that are going to follow it, we're going to start talking about differential equations. Now, we've already seen differential equations a little bit before when we were talking about exponential functions. In particular, this led us to discuss what were called separable differential equations. Now, in this lecture today, I'm going to introduce general first-order differential equations. And I'm going to show you how you can analyze these things in general and how you can picture their solutions using slope fields. As we progress in the following lectures, we're going to talk about how we can use integrals to numerically estimate the values of these or the solutions to these differential equations using, say, Riemann sums. And then we're going to look at how you can solve these completely using pen and paper methods using integrals. And what this will use, or what this will employ, is our previous techniques for solving all of these integrals that we've been building up over the past series of lectures. So let me start by introducing the general form of equation that we are going to be interested in today. And that is what's called a first order, so first order differential equation. Okay, so in complete generality, we can write this as saying the derivative of some function with respect to x is equal to a function of x and that unknown function y. So what this tells me is that if you think of this, say, in terms of a physics problem, if I know, say, position y at x, then I can compute its derivative as well, its slope, its velocity. So sometimes you'll hear people refer to these types of equations as velocity fields, and that comes from the fact that on the left-hand side, if you are a physicist, you would interpret this thing as being the velocity of your unknown y. Now, this might look a little confusing, but everything is just, y is equal to y of x. We're always just asking ourselves, what is the function that satisfies this differential equation? And it's called a differential equation because it includes a derivative. That's the derivative of y with respect to x. Now, also, this is called first order because it includes derivatives or just the first derivative. So for example, I could instead give you what's called a second order differential equation, which would be a function, say, for the second derivative. So in this case, it could be, let's call it g, so we don't confuse anyone, some function of x and y, and maybe even it includes the first derivative. Now you can see things get very, very complicated, right? This is now a function that gives you, again, if you're thinking in terms of physics, the acceleration of an object in terms of its position and velocity. So second order differential equations are beyond the scope of this class. We are just going to talk about first order differential equations here. Now, sometimes you'll also see them written like this. You can see people write y prime is equal to f of xy. Just like how we have all kinds of different ways of writing the derivative. Sometimes we use Leibniz notation, that's dy dx. Sometimes we use the prime notation, that's y prime. The same thing works for using differential equations or for writing these things down. And so what does it mean by a solution to this equation? Well, a solution, y is equal to y of x, satisfies, well, if you take the derivative of that function, this has to be the right-hand side, f at y of x, for all x in the domain. And typically the domain will be specified, or at least you'll have some idea of what it is. But this is just left side function equals right side function, nothing more. Now, in general, differential equations are a relatively difficult thing to solve, especially explicitly. They're like most integrals. We don't have a general sort of answer. If I just write down a random function, I say, find the integral of it. There's often no way to do that. We have methods for select ones. Same thing goes for differential equations. And it turns out that they're related. These are sort of the same problem, just disguised. But the nice thing about this is that if I give you a function and I claim that it's a solution to a differential equation, you can check just by taking a derivative. So let me give you an example. Let's say show that every member of the family of functions and the family of functions will be given by y is equal to a constant divided by x plus 2 is a solution of the first order differential equation let's look at this. So this is dy by dx is equal to 1 over x times 2 minus y. So that's my general function on the right-hand side. And in this case, we're going to say that the domain is going to be the interval 0 to infinity. As you can see, my function and my differential equation are not defined at x equal to 0. And where c is any constant. So how do we check if y equal to c over x plus 2 is a solution to this differential equation? Well, if I take the derivative of y with respect to x, that should equal to the right-hand side of the differential equation, 1 over x times 2 minus y. So essentially, this becomes sort of like a left side, right side problem. So left side. Okay. So then that tells me, first of all, if y is equal to c over 2x plus 2, then dy dx, I just need to take a derivative of this thing. So I'll just write it just so that we know what I'm doing. This is given by minus c over x squared. Okay, then let's turn to the right side now. And on the right side, I get if y is equal to c over x plus 2, then the right-hand side was 1 over x times 2 minus y. Let's plug in for the function y of x. I get 1 over x, and then c over x, it's 2 minus c over x plus 2. You can see that those 2's are going to cancel each other out. And on the inside of the brackets, I get minus c over x. And so this gives me minus c over x squared. But this tells me, therefore left side equals to right side. Left side equals to right side. So this tells me that if I take the derivative of my function that I was given, y is equal to c over x plus 2, the derivative of that thing is equal to exactly 1 over x times 2 minus y. So therefore, this function satisfies my differential equation. This is a solution to the differential equation. In fact, this differential equation is separable. So you can go back in the notes and you can actually find this solution, y equal to c over x plus 2. The c is going to come from integrating, right? We've seen this over and over and over again. And so if you can go back through the notes and you can try and solve this thing using those methods. Now, one thing that we saw briefly with our initial discussion of these differential equations was that we can pin down an exact value of C as long as we know a point on the curve. So let's discuss this for a second. We have a general solution that is all possible solutions. That's all possible constants. But then we have what's called a particular solution. And a particular solution is a solution y of x to the differential equation this, satisfying y of x naught is equal to, or yes, y of x naught is equal to y naught for some x naught and y naught. So you can think of this as being sort of like an initial data problem, right? So if you're thinking of this as sort of finding, if you know the slope or the velocity of your object in terms of where it is in space and at sort of what x value. So if you think of that as time, as when, then you need to know a particular value. So when I started at x0, then I know that my position was 10, whatever it was, right? That would be my y0 value. So that allows me to pin down a particular solution. So remember, if I just sketch this out again, if I have c over x plus 2, that was from the previous differential equation. If I restrict to some x0 value so that I have to have some y0 value, that will pin down the value of c that I have to have here, right? So if, for example, I want y of 1 equal to 0, this would give me that 0 is equal to c over 1 plus 2, which tells me that c is equal to minus 2. So I get a particular solution of minus 2 over x plus 2. That's the particular solution corresponding to the measurement that I'm providing it. At x equal to 1, I get y is equal to 0. And then sometimes what we like to do is we like to couple the differential equation with our data. So we call this a first order initial value problem. So you'll see this abbreviated a lot of the time to IVP. That's an initial value problem. But basically, you're going to be given a differential equation, and you're going to be told that the solution has to go through some point. So this allows you, or this sort of forces you to solve the differential equation and pin down a particular solution altogether. So for example, again, without solving these things, we can say, I can ask you questions like, show that the function let's say y is equal to x plus 1 minus 1/3 e to the x is a solution to the IVP initial value problem. And this initial value problem will be dy by dx is equal to y minus x, and y of 0 is equal to 2/3. Well, we're going to basically do the same thing that we did before, and we're going to, on top of that, check whether or not we actually go through the point 0, 2/3. So let's start with left side. In this case, we get the derivative of y. This is equal to the derivative of x plus 1. Let's put all this in square brackets, minus 1/3 e to the x. which this should be relatively simple for us. So 1 minus 1/3 e to the x. And similarly, the right side gives us, we have y minus x, which is equal to, let's put this all together. So here's the function y. And then subtracting x off that, well, that just gives that the x's are going to cancel. So that and that cancel. And so we get 1 minus 1/3 e to the x. And so because left side is equal to right side here, we do in fact have a solution to the differential equation. But that wasn't the question, right? The question is it a solution to the initial value problem? Which means it has to be a solution to the differential equation, and it has to go through the point that we are prescribing it goes through. So now y of 0 is equal to, well, in this case, it's going to be 0 plus 1 minus 1/3 e to the 0, which is 1 minus 1/3, which is 2/3, showing that y of 0 is equal to 2/3. And therefore, y equal to x plus 1 minus 1/3 e to the x is a solution to the initial value problem, IVP. Right, so it's just a plug and check problem. It's a left side equal to right side problem for checking if you're a solution to the differential equation. And then it's just plugging in the value of x0 and making sure that that's equal to y0 if you would like to show that this is satisfying your initial value or it's a particular solution. Okay, so it's hard to say in any real generality how you can solve differential equations. But what I would like to point out is that if we have a differential equation, say that looks like this, this basically tells me that if I know the value of x and I know the value of y for my function, then I know the slope of the function at that point as well, right? Because that's what the derivative is actually equal to. And so let me illustrate just by finding what the slope is, and then I'll show you how you can use this information to figure out what the solution of the differential equation is without actually, say, just writing down y is equal to x plus 1, whatever. Okay, so a lot of the techniques that we have to use here are numerical in nature because like integrals, we don't have explicit solutions. So let me show you first how you can use this information analytically. So for the differential equation, and let's say dy dx is equal to 2y minus x, draw the line segments representing the slope field at the points, let's say 1, 2, 1, 1, 2, 2, and 2, 1. Okay, so the first thing is we have this word or this phrase slope field, right? Basically what this is going to be is drawing all the little tiny tangent lines. And we know that the tangent lines, the slope of them are given by this differential equation. So let's do something here. So we have, say, x, we have y, and what do we have? We have, say, 1, 2, 1, 2, and we have the 4 points on this square. So basically we want to know if we have a solution that goes through one of these points, what is the slope of the tangent line to that solution at that point? Well, okay, so let's list the points. Let's make a little table, points and slope. Okay, so start with 1, 2. Well, in this case, the slope is equal to 2y minus x, which is equal to 2 times 2 minus 1, which is equal to 3. So it's positive. That means that the function is increasing. And the value of 3, it doesn't mean as much as if it's positive, right? Because these are just going to be sketches. In our case, we're mostly interested in sort of increasing or decreasing, as is mostly the case when you're sketching. Okay, 1, 1. In this case, you get 2y minus x is equal to 2 times 1 minus 1. And in this case, it's equal to 1. So again, increasing, but not as much as it would have been if you were at the point, say 1, 2. All right, how about 2, 2? You get 2y minus x. So again, this is just the right-hand side of the differential equation. 2 times 2 minus 2. So in this case, you're getting a positive slope of 2. And finally, 2, 1, in this case, you get 2y minus x. This is 2 times, 1 minus 2, which is equal to 0. Okay, so let's sketch in our little tangent lines here. And so at 2, 1, let's work from the bottom up. You get a 0 slope. So your line is horizontal. So we would draw the slope field with a little horizontal line there. I know that it's not perfect, but okay, at 2, 2, we've got a slope of, say, 2. So maybe we're going to just try and draw these things so that they're relative to each other. At 1, 1, we've got a slope of 1. So this should be a perfect 45-degree angle. And finally, at 1, 2, we've got a really steep one of 3. So the point here with the pictures is just supposed to be that at, say, 1, 2, it's steeper than at 2, 2. Okay, that's all I'm trying to emphasize with this. Now, this might not look like it's particularly interesting or particularly useful, and I might be inclined to agree with you, but that's because I only have 4 points on here. How about we let a computer take over for us? So let me share a different screen here. Just a moment. So it turns out that you can do this in Desmos, and with Desmos, you can get it to plot all of these little slope lines for you. So what you can see on the left-hand side is I typed in my differential equation. So it's saying first order differential equation, dy dx is equal to, in this case, they call it g of x. That was just what it loaded in as. And then I'm going to write in my differential equation, 2y minus x. That was the equation we were working with. Well, then here, now you can see all of those little tangent lines, and it's giving you a slope field for this. And so what you can do is you can sort of follow these little lines, because these lines are pointing you where the function is going. So for example, if I started somewhere at -2, 0 here, it's sort of shooting me up. And now I can see that it's shooting me up and up and up and up and up and up and up. Similarly, maybe if I start at 1, 0 here, it's shooting me down. Let's see if we can move that. And you can see that it would maybe follow the green, and it's shooting me down and down and down and down and down and down. Now, even that is relatively hard to see, and I understand that. So what's even better is that there's a lot of numerical aid that can actually plot the function on there for you as well. And so I'll include both of these websites in the description for this video, so that you can play with these on your own. So for example, this one is a slightly more complex version of this. So the first thing that we want to do is we want to put in our differential equation. let's restrict our x values, our plot, to be between, say, -2 and 2 for both x and y. Now, you can see you've got the slope field in here. You've got all of those little tangent lines sketched out. And remember, actually, maybe if I go back to -3 here, the first initial condition I was interested in was -2, 0. So if I click on that point, it sketches out what the solution looks like. And so what it's doing is it's following all of these slope lines. And we're going to talk about how to come up with these solutions numerically in the next video. But for now, just sort of observe what's happening. Similarly, I had another one. I think it was around 1/2 and 0. If I click on that, I can see that it's pulling me down into the negative numbers. Now, what this thing is doing is it's finding the whole solution that goes forwards and backwards in x values. Okay, so I was just looking at what happens when you go forward, but it's plotting the whole function for me. And in this way, you can start clicking on, say, sort of random values to see what the function looks like that goes through each of these points. You can also come up with maybe more complicated systems, and you can ask yourself, what does the solutions look like here? In this case, maybe we should refresh this so that we can start completely over. So we get, say, what was it? 2y minus x squared. Let's go between -2 and 2 again, just so that we're sort of zoomed in on a particular region. And you can do the same thing. So you can just pick some points and you can ask yourselves, what happens? What do these solutions look like? And unfortunately, even with this simple looking differential equation, I'm not sure that we have an exact solution. I'm not sure I can just say, okay, the solution for you is going to be y is equal to blah, 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 right? But what we can see here is at least a picture of what's happening. And what you could use this knowledge for is you could say, okay, well, if I start at, say, -1.51, well, it looks like my function is going to go off to infinity. Whereas if I started at -1.5.5, it looks like my function is going to go off to -infinity, right? So we can get some general ideas of the characteristics of these functions based on where they're starting. And you can very easily pick these starting points by just sort of clicking anywhere on the graph. Okay, so that was a sort of a very quick and dirty introduction to what we're going to talk about for the next few lectures here. In the next lecture, we're going to introduce something called Euler's method, and it's a way to numerically approximate these solutions. Now, because it's numerical, that means we get, say, at x equal to 1, the solution is 2. At x equal to 1.1, the solution is 2.1. It's not going to be a nice y is equal to x squared or something like that. It's very similar to what we've been doing with Riemann sums. So this is how we can, say, feed it into a computer to approximate these things. And it's how those pictures were drawn for you on that slope field that I just showed you.